Hi there, I'm Noah Goodall.
And I'm Daniel.
And today we have a lovely presentation on vehicle suspension. And we're going to start out with a nice intro video for you guys.
Hi there, I'm Noah Goodall. For the next 15 to 25 minutes, we're going to take you on a fast and loose joyride through the wonders of vehicle suspension.
And I'm Daniel. Today, you'll learn just how simple it is to model your very own vehicle's ride quality using differential equations. We'll take you through the ins and outs of springs, damping, and how to do some sick burnouts. Buckle up, baby.
All right, that was planned. So, with that in mind, vehicle suspension. What does it do and why? Well, suspension, or shock absorbers as they're more commonly called, are designed to smooth your vehicle's ride and keep traction with the road. The suspension system is made up of two main parts. The outer spring, which is just a large coiled piece of metal, when compressed or extended, compressed by a bump or extended into a hole, will raise or lower the vehicle, fighting these forces, keeping the tires on the road.
And what's in between that spring is a damper system. So what it is that basically the most simplified way we can get it is a cylinder with a very viscous fluid within it. And there's a piston that's driving up and down in it as the white wheels compress and decompress. And so through that piston, there at the top there's a disc. And in that disc there's very many different ways to get the fluid to go through it, but in the most simplest way there's holes, and the viscous fluid has to be forced through those holes, slowing down how fast the spring will decompress or compress.
Very good. Right here you can see our cars, which we'll be using as examples for some measurements throughout the video. And right here is a picture of my car's suspension. You can see the outer spring, and inside there is the damping cylinder.
So what we did was we got three cars for you guys. We only showed two here, but this is Noah's car, this is my car. This is in the 1990s, this is the 2000s, and the car we got next was a more recent car in the 2010s. So here we have a couple of assumptions first. We have damping is going to be constant. So in the newer cars now, they have some new technology where in the damper, they have a way that the damping will increase depending upon how much pressure it receives. But in terms of our project, we're going to keep it constant. At equilibrium, when your car's at rest, when the car's off, you're not driving it, the distance that the spring traveled is going to be zero. We're going to set that to be zero. That's equilibrium. And in our cars now, it's not really an assumption, but it is known that our cars are over-damped. Why? Because we would like to have the smoothest rides when we drive. So
and we'll explain that more a little bit later.
Exactly.
So next, we're going to first talk about the outer portion of the suspension, which is the spring. So beginning on this demonstration, we have Hooke's law. Hooke's law is the force output of a spring is equal to a spring constant times x. X is the distance that your spring has either been compressed or extended. And now we have a short video that will go into a little more demonstration. Yeah, there we go. And it has some nice, peaceful, classical music for you. So right here, you can see these three models right here. This is an empty spring just hanging in the air. This right here is a spring that's under a constant weight. And this guy here is a spring that's under a constant weight and an external force. This is A, this is B. We're going to start with A. A is just very simply Hooke's law straight and forward. Force of the spring equals a constant times the distance that it has extended. Now this system here is in equilibrium. What that means is that due to Newton's second law, the sum of the forces are zero. So even though there's a force of gravity pushing down on the spring responds with an equal force making 0 total force and 0 movement. This is like your car sitting in a parking lot. It's not moving around, it's just staying there. So you can model this with Hooke's law, saying that the force of the spring equals the spring constant times the length. What does this mean in straight, plain forward English? Once I finish drawing my lines, I'll tell you. The spring force that is responding to outside pressure is proportional to that change in length. So as you push the spring more and more, it responds with more and more force. So let's look at a more complicated example that will show that in depth. In number B here, we have the force of gravity plus the external pushing force, which will extend it both distance L because of gravity and X because of this pushing force. So here we have gravity plus the external force is proportional to the length because of gravity and the length because of the external force. This external force might be a bump, it might be a hole, it might be someone hitting your car with a baseball bat. Who knows? Now, what you might not have noticed is that this right here can be seen as a homogeneous second-order differential equation. If we bring this right side over to the left side, we'll have it equal to 0, which makes it homogeneous. And so now we have the force of gravity plus the external force minus the force of the spring will equal 0 total force. We can simplify this even further by saying that in example A, the force of gravity was exactly canceled out by the force of the spring due to that length L. So if we rewrite this, putting those two values next to each other, got a little finicky with my notation here. This is mass times the gravitational constant, which is the force of gravity, minus the force of the spring due to gravity's push is 0. So very simply, in a car, you have an external force hitting your tires minus the force of the spring will equal 0 force. And we will continue on with this equation and add more things to it as we go along. And now I'm just sort of writing it in the proper format so that you can recognize it as a second-order differential equation. It's a nice 1694 classic there, my favorite.
It's a good presentation, right? I like it too.
I think it's pretty good,
Do you
don't
know
you?
the composer?
Yeah, Pascal?
Yes.
Yeah. That's it. All right. So now we look at our car's springs specifically. Due to Hooke's law, like we've just said, the force of the spring is the spring constant times the distance that the spring has traveled. So you can go outside right now and find the spring constant in your car, or heck, in any spring if you wanted to. Now my car, the 1999 Ford Escort, it's a sweet car, let me tell you. What we did to find this was we took a weight, our Daniel, we placed him in the car, and we measured the distance that the car sank downwards. So we found that Daniel's weight is 686.7 newtons
150 pounds.
equals our spring constant, which we're trying to solve for, times the distance that it traveled downwards, which was 0.01984338 meters. This right here is in units of force per distance, newtons per meter. So the more meters you multiply it by, the higher force you get. So we found that the Escort's spring constant is 34,605 newtons per meter. What this means is that if you were to go outside and compress this spring 1 meter, it would respond with 34,000 newtons of force. Now you might not really picture what that might be in your head, but 34,000 newtons, 1 newton is about a quarter pound. So that divided by 4, that's how many pounds of force are going on in your springs. We did the same experiment with a more modern car, the Volkswagen GTI, and we found that it has much better suspension than mine at 144,000 newtons per meter. I might want to get that checked. All right.
All right.
I think it's you now. Yes, it is.
All right, so now we're dealing with what's inside of that spring. So we have, like I said before, it's a cylinder and it has some viscous fluid within it, and the piston is moving in and out of it. So I'm really excited about this because I got to work with a fellow friend of mine, engineer at UF, and his name is Nathan, and I sat with him and we created this together, and I think it's awesome. So let me show you guys. So this is, he's gonna show you where it is in the car. There's 4 of them, of course, but here it is, right? And this is the most basic model. This is how it functions. The piston is that rod in the middle is going inside the cylinder that I was talking about. And here's the blue is the fluid that I was talking about. Now it may not be blue, but it's just to represent fluid. And those are the holes that I was referring to earlier. That viscous fluid has to be forced between those holes, slowing down how fast the spring moves up and down, right? So now, this is what damping is. And so we're gonna get into the math behind all of it, the differential equations behind it. All right, we have this video for you explaining it.
All right, so now starting from where Noah left off, he gave us one of the forces of the spring. But now what we're gonna do is we're gonna get up all the components that we need, put it together, make our differential equation, and solve it. So starting with Newton's second law, we have the sum of all the forces equal to mass and acceleration of the system. What is the sum of all the forces? The sum of all the forces are gonna be the force of the gravity, force of the spring, which Noah gave us, force of damping, and the force of all the other things that may happen to the car. We're gonna call it force of external, equal to the mass and the acceleration of the system.
Tell us, Daniel, what might force external be?
Force of external is anything else that may happen to the car. It can be rocks, it can be gravel, it can be speed bumps, it can be an incline, it can be how fast you accelerate your car, how fast you decelerate your car, things like that. So whatever is happening to the car, that's what force of external is going to account for.
Thanks, Daniel.
All right, so now, force of gravity is mass times the gravitational constant. Noah gave us the force of the spring. I'm giving you the force of damping and the force of all the other forces outside the car. These two forces, the force of the spring and the force of damping, are negated. Why? Well, they're negated because they're restoration forces. So whatever way that the car is moving, they're countering it, right? So now let's put these together. We distribute the K constant, and we get mg minus KL minus Kx minus d dx dt plus the force of all the other forces. So now, what Noah told us was, at equilibrium, this right here earlier was 0, and it's still going to be 0 here, right? So that's 0. So that's not going to come up anymore. That's gone, and we're left here. So let's simplify. What I'm going to do is I'm going to add these two over to the right side, leaving all the other forces by itself. So we have mass times acceleration plus the K constant times x plus our damping constant times the velocity of the spring, equal to all the other forces. And to get it visually into a differential equation that we're familiar with, we have it right here, right? We change a to the second derivative of x, and we have them in decreasing order. So this is a second order differential equation, and it's constant coefficients. That's going to be very important later on. All right, so now we need to decide whether solutions even exist for these type of differential equations. And fortunately for us, by Cauchy's theorem, we have to prove 3 conditions, and yes, a solution will exist. So now, the first condition, our differential equation has to be continuous on our interval, I. What is our interval? Well, our interval is going to be in terms of our variable, which is t. In our differential equation, all the derivatives are with respect to t, right? Right here and right here. So now, t is never negative, so that's why our interval is from 0 to infinity. Second condition, in our interval, our leading coefficient would have to remain non-zero. The mass of our cars is what the m represents in our differential equation. Therefore, the mass of our cars will never equal 0. Hopefully, none of your cars equal 0 in terms of mass. Our third condition, our initial time must exist in our time interval. Our time interval is always positive. We're never going to have a negative time. Therefore, these 3 conditions, 1, 2, and 3, are all checked. Therefore, by Cauchy's theorem,
a unique solution exists.
Now that we know a solution exists, what is our solution? Well, our differential equation is non-homogeneous. With that being said, non-homogeneous differential equations with constant coefficients, we can utilize the superposition principle. What is the superposition principle? Superposition principle is saying that our solution is going to be a factor of two components, our complementary solution and our particular solution. Our complementary solution is just the solution of our differential equation without the outside forces. So it's a homogeneous solution. Our particular solution is going to account for that missing forcing factor, which was our forcing function, which was the force of external. So now, when a particular solution accounts for it, how does it do that? Well, it takes the form of the forcing function, whether it be constant, linear, quadratic, whatever it is. Our particular solution is going to take the same exact form. But we're going to get into more details about that later. Our first step in solving this entire differential equation is to get the complementary solution. All right, let's go do that. Now, we set it equal to 0, because that's what we need to do to find our complementary solution. When we have constant coefficients, so now this is where I said it was going to be important. When we have constant coefficients, mass, damping constant, spring constant, and you have a second order differential equation, we're going to have a characteristic equation. What does that mean? Well, we're going to take the derivatives, the order of the derivatives, and set those as the power of a variable. Variable could be anything. I could have put A, B, C, D, or E, F, any number, any letter I wanted to. But we used R because I'm used to Dagan using R. All right, so now we have mr squared plus dr to the first power plus k. There is no variable here because there was no derivatives of x in our differential equation. Now we have a simple quadratic equation. I usually like to complete the square, but in this case, with different factors such as m, d, and k of different cars, all our different cars, we're going to have the quadratic formula, which works for all of them. So now, what's important about the quadratic formula is the discriminant. The discriminant is d squared minus 4mk. It's whatever is underneath the square root. When this discriminant is greater than 0, we're going to get two real solutions. When it's equal to 0, one solution. When it's less than 0, we're going to get two imaginary solutions, which are complex conjugate solutions. Why is this important? Well, as a reminder, as we reminded you guys earlier, damping is constant at rest x equals 0, but now our cars are overdamped. When our cars are overdamped, that means we have two real solutions. That means our discriminant is greater than 0. So in terms of solving this differential equation, we can proceed knowing that we're going to have two real solutions.
You could pause that for me, Daniel. So what overdamped means, there are three options in a damping system. Overdamped is what you want. Critically damped is and underdamped is bad. Okay? Overdamped means that damping constant is much greater than your spring constant. So if you were to draw a graph of the length, the position of the spring over time, say you hit a bump, so you're up here, and the spring is compressed or extended. In an overdamped system, because of that viscous fluid flowing through the valves in the damping chamber, it will nice and slowly drift back down to an easy equilibrium. In a critically damped system, it's just on the verge of being underdamped. So it'll work, but you're gonna go back down to equilibrium. In an underdamped system, it's doing nothing, okay? You hit a bump, this is gonna go woo, and way down there, finally, it's gonna go back down to equilibrium. You're gonna get what's called an oscillation. My car actually, a couple years ago, had this problem where it's a very old car, and the suspension was beginning to fail. So every time I went over a bump, the car would just, slowly rock back down to equilibrium. So you want overdamped.
Thank you. All right. Let's get back to this handsome fellow over here.
Leaving where we left off before, our dampers are different when they're overdamped, critically damped, and underdamped. That means the viscosity of the fluid that's in our suspension, that's in that chamber, is going to be thicker in the overdamped. So when we set our discriminant greater than 0, overdamped, we're going to solve for the viscosity of the fluid. It has to be greater than 2 square root of m mass times the k constant. Now if I do this for the critically damped situation where it's equal to 0,
I get that the critically damped fluid constant is equal to 2 square root of n times k. Now, why is this important? Well, this is just visually showing you that our D, the viscosity of the fluid in most of our cars right now as they are going to be greater than the critically damped version of them. That's all that's really showing. All right, so now we're going to proceed where we left off in terms of this quadratic equation. This quadratic equation breaks up into 2 solutions, right? One with the plus and one with the minus. So we're breaking up the plus or minus operator. And now this is going to leave us with a solution of x of t. And as solutions, right, these are solutions. So now, to utilize these solutions, we put them in the form C1 times e to the power of R1 times t. That's the first one. Then we add C2 e R2 times t. Now this is the solution of our homogeneous differential equation. This is when it was set equal to 0. This is the solution of that. Now what we need to find is the particular solution that's left, right? As you guys remember, the total solution is going to be x equal to x complementary plus x particular. So really and truly, let's write this as the complementary solution. That's what this is right here. So now what we're going to solve for now is to get a particular solution and then finish off with that. All right, so before I continue, or he continues, I just wanted to say that the R1 and R2, you can solve for that in the solutions prior, R1 and R2. Really, to solve it into a finite number, you plug in your mass, you probably Google that. You plug in your K constant, which Noah showed you how to find, and your damping constant, we're going to show you how to find later on. All right, so you just plug those in, you solve the equation, the 2 solutions, you get R1, R2, and you apply initial conditions for C1 and C2. Over here. All right, so our particular solution, as I said earlier, is really accounting for the forcing function, force of external. It's accounting for it. And how does it do that? Well, it takes the form of it. So whatever the force of external is, that's the same format is going to be used for the particular solution. Well, our force of external is not something that we can just grab or something that we can measure. Well, it's very arbitrary. So that's why we have all these different functions that the force of all the other forces may be able to equate to. So these are all the possibilities of them. And correspondingly, when you have different possibilities of them, we're going to have different solutions for them. Right? Because a constant, let's say that's one rock you hit on the road. But maybe your speed bumps, maybe you go over a series of speed bumps, maybe that'll be over here with the cosine and the sine as it's a wave. Or you hit a very sharp bump and it has to be represented by E. Who knows? But whatever it is, it can be accounted for in our particular solution. That's why when we come to our final solution, x equals xc plus xp, our x of c is already accounted for, and this is going to be arbitrary all the time. So with it being arbitrary, instead of leaving it as force of external, which is notationally incorrect, you don't want to put force of external, that's why we leave it as a particular solution, right? And we're just going to rewrite that here, and that's why this is our complete solution of our differential equation. It's a non-homogeneous differential equation, so we're not going to have a concrete answer. It's going to vary, but this is the most varying factor. And to get your R1 and R2, you're going to have to plug in the values such as your damping constant, your spring constant, and the mass of your vehicle. Right? And that's our final solution. Thank you. All right. All right, so this was just a slide to show you the final DE again, but we've already been through this. We solved it in the video, right? So we're just going to skip this slide.
Okay, so to find our car's damping constants, we could perform an experiment that was very similar to the one that we did with Hooke's law, where we put a mass on the car, we release the mass, and then we find the change in distance over time. So if you can play that video, very simply, all you need is two guys and a tape measure. One to sit on the trunk of the car, jump off, and you measure the change in distance over time, meters per second. So we found that the velocity of the Escort spring was faster than the velocity of the Volkswagen's, the newer car. You might think that that's good for the Escort, but it's not, because you want that reaction to be slowed down, smooth, over damped. If you wanted to solve for your damping constant, you go back one slide. So to solve for your damping constant, you would plug in all the things you know: the mass of your car, the damping constant, or the spring constant, the length that it sinks down because of the mass of the car, the length that it would sink down under a force, and your velocity, and any external force that you're going to have on there. Now, because we will imagine that this is at equilibrium, the force external won't be there, so then you can just plug in the gravity, the spring information, the velocity, and you could just use some simple algebra to solve for your damping constant. We actually did this, but we found that our measurements were not incredibly accurate, because you would need some equipment that's a little out of our price range to measure exact, velocities and weights and things. So we'll leave that to your imagination. And then from now on, we did some experiments to model just how suspension will work in some real-life situations. Up at this top video, you can see on rough road, the car sailing across this very bumpy road, it looks pretty stable while the wheels are jostling around. On the bottom video, you can see I'm going a little slower, and you can see the wheels rocking up and down while the body of the car stays fairly level. The purpose of suspension not only is to make your ride smooth so that you're not bumping up and down with the road, it's also to keep your wheels stuck to the road. If your wheel goes into a hole in the ground, the wheel will extend down to match the surface of the road. This will help you to keep traction so you don't skid out, so that you can turn even when the road is uneven. Then we did an experiment on inclines, and we found that on a hill, which is actually just off of the I-75 exit coming onto Williston, we'd been eyeballing this hill for a while, so we decided to use it. The incline of the hill was 7.5 degrees, but the incline of the car sitting on the hill, we used a little digital protractor, was a degree more. So as you're just sitting on the hill, the chassis of your car is leaning backwards, but the suspension makes sure that the wheel stays on the ground and keeps traction. So although the car's body leans backwards, suspension keeps it on the road.
And this was very fun to do, actually. I just want to say, I chose this hill because every day after leaving class and coming home, eyeing down that hill was just the best part, because I would come up at this intersection back here, and I would sit there, and I drive a stick shift car, and it's super fun to imagine what we did in the experiment, to sit on that hill and let your car roll back, and the stick shift car to roll back and to accelerate, and getting these measurements was really fun in terms of driving my stick shift car, so I was really excited about that experiment.
And next we see an example of acceleration. When you combine these forces, say you're on an incline and you accelerate and there's bumps in the road, your car wants to flip over backwards. It wants to lose traction. Your suspension keeps that from happening.
And this was the third car I was talking about. This is a 2015 car that we are able to get. It's actually my dad's car. And so I had to make sure I took good care of it. He doesn't know about any of this until he sees the video.
This on the back road.
I'm gonna have to talk to him about this afterwards. So. Oh, and when we were trying to raise in our car, we had the digital protractor again, like we did on a hill, and we kept accelerating at the beginning so that we can try to raise up our max incline, how far back the car would lean back in terms. So we got it to be the highest at 28.9, and I think this video was the one that we got it to be 28.9. It might be the one.
Make sure it's not muted.
Now, I would have had a lot more fun if I had my stick shift car at the time, but I didn't.
And you can see the car, it's very slight, but you can see the car raising up ever so slightly while the wheels stay on the ground.
Don't try to do this.
Don't try this at home, kids.
Buckle up. I warned you at the beginning.
So that pretty much concludes our presentation, and we just have a little
video for you.
Outro video for you.
Always something else. Gotta go. Oh, thanks for joining, by the way. Pleasure.
We hope you've learned a few things about differential equations. We also hope we're getting an A. See ya.
My favorite part. I don't like this part. Well, that concludes our presentation, guys, so that's it.
I got to edit this, so I got to put